Yes, Manoj is always. Hmm.
Hi, good evening. Can one of you confirm if I'm audible?
Yes, sir, you are audible.
Thank you.
Good afternoon, Manu. Are you there?
Yeah, good evening, Professor Pradeep. I'm here. Yeah.
Okay, yours. You are the first one.
Yes, I am the first to go. So I
Very good.
thought about some of the ideas you gave, putting the grand challenges in the field and also I have reworked my talk, keeping all that in mind.
Very nice. Very
That's
nice.
quite-
Overall, the time that is available, we should ask some,
Yeah,
use it
right.
well. Yeah.
Yeah. But that's quite refreshing to think about all these things, because where you place your work in context of so much other things which are going on. And
Absolutely. Absolutely. Yeah, it's important. Arti, you are there?
Yes, sir.
Oh, very nice. Good. Very glad.
Hey, brother. Good evening.
Yeah, very nice. Srinivas. Good. Who else is speaking today?
Rajneesh Kumar, right? Third speaker today, Rajneesh Kumar.
Yeah, Rajneesh should be around. Yeah. My office called all the people, so you must have also received.
Yeah, we got the call. So.
Yeah, so that should be okay. Yeah, we have a couple of. Let me make sure that Rajneesh is there. So. Rajneesh, you will be joining, right? Okay, just wanted to ensure that people are all there, and yeah, that's all it is. Thank you very much.
Yeah, sure. Okay.
Yeah, very nice to see several of our colleagues joining. So it's good. So maybe we'll wait for one more minute. Is that okay? One more minute, probably. Manu will one more will maybe. I don't see him now. Yeah,
I see Manu. Manu
yeah, I'm here.
Very nice. Okay, then I think we will get started. I'm not going to give any introduction, so we have enough time. So whatever, that's 25 minutes and then, or 25 minutes, and then have discussion. Let's get going. I will give you a warning or alert or something when the time is up. Yeah. Manu?
Okay, so I'll share the screen.
Sure, we can see.
Okay. So good evening all. I'm Manu Jaiswal from the physics department, and I will be talking about some interesting problems on mechanical instabilities and transport phenomena in two-dimensional systems. So a quick outline, I will talk about my motivation, what got me interested into these kind of problems, together with grand challenges in the field, and that makes up about the first half of the 20 minutes. And in the remaining time, I will show some representative research work done at IIT Madras related to the mechanics of membranes and how transport, electrical and thermal transport happens through the system. Quick introduction is this small honeycomb is my research area, and this is me, and it would not be interesting enough if I just talk about this. Unless I talk about the broader research area, I would not be able to convey the excitement in the field. There is one more motivation why I made this sketch as an introduction, and that has to do with this honeycomb lattice. This honeycomb lattice is the lattice, the crystal structure which graphene has, and that is one of the primary materials whose properties I would be discussing today. I'll start with the following, that graphene is a two-dimensional electron gas, and if you make a Hall bar with it and cool down to low temperatures, say 4 Kelvin, and apply a very large magnetic field perpendicular to it. How large could be 10 Tesla, 14 Tesla. For people who are not into this, I'll just remind that a Tesla is many orders in magnitude larger than the Earth's magnetic field. In fact, 10 Tesla is like 7 orders larger than the Earth's magnetic field. If you apply that large magnetic field, then you get these oscillations in the longitudinal resistivity, which are shown here. And you also get very precise plateaus in the Hall conductance. And in fact, this has become the definition of 1 ohm, the amount of Hall conductance you have, because that is defined in terms of the units of E square by H. So this is all very well known, and I'll just tell you a short story how I got interested in this field. About 10 years back, when I was doing my postdoc at NUS Singapore, we were doing one of these routine experiments. The routine experiment involves you take one of the graphene samples and sweep your gate voltage. So in this transistor, when you sweep the gate voltage, and now you look at the band structure, the Fermi level goes into the conduction band or goes to the valence band. And as a result, the resistance increases when it is close to the Dirac point here, and then decreases on both sides because both holes and electrons can conduct. So this is a typical resistance versus voltage curve you measure at room temperature. And we cool down, measure the resistance versus voltage at low temperature, and then apply a magnetic field and measure what kind of quantum Hall effect is present in the system. In this particular late night experiment I was doing, I measured this curve at room temperature, then I cooled down, and I realized that there are some oscillations coming, very periodic oscillations coming in the plot. And that struck me, maybe I forgot to take the zero field data. So what I should do is switch off the magnetic field, first record the zero field data, and then switch on the magnetic field. I got up to do that, and to my shock, the magnet was already switched off. There was no magnetic field applied. And remember this, there is no small leakage which can be responsible for this. This behaved as if a giant magnetic field was passing through the sample. the positions of these oscillations were exactly where you would expect them if a large several Tesla magnetic field was passing. And this phenomena had a connection with some theoretical predictions and a related experiment. I made a record of this in my lab book, Zero Field Quantum Hall Effect from Pseudo-Magnetic Field. And we could not publish it because it was not a reproducible thing. We got it by accident. But this is probably the only known record I know of a transport experiment showing zero field quantum Hall effect. How does this effect arise? People have seen the same using measurement of density of states, using scanning tunneling spectroscopy in accidentally grown bubbles. So if you take CVD graphene on platinum, then you get these very sharp bubbles that you can see in this picture here. And experiment has revealed that the magnetic field, not the real magnetic field, a pseudo magnetic field as giant as 600 Tesla can be present at these sites, and which is also confirmed by theory because this samples are highly strained. The membrane is highly strained at this location, and that a strained field translates to an effective gauge field in the Hamiltonian, and that is responsible for this very unique phenomena. While these things have been shown and they are exotic quantum phenomena, but people still lack any means of controlling the membrane mechanics. If you ask me, can you create this again? It's impossible. You can't dictate how the membrane should have a particular shape. It's a grand challenge in the field to develop control on the membrane mechanics in order to realize these very novel phenomena. This has given birth to ideas such as origami and kirigami electronics. Origami, as you know, is the art of folding paper to create all these beautiful structures that you see. And if we could do the same with membranes, atom thin membranes, then we could realize entire circuits which have not only high mobility transistors, electrodes, but also built-in pseudo-magnetic fields which can't be achieved with a superconducting magnet. Yet we are nowhere close to doing this in a reproducible manner. One or the other experiment here or there has shown this. Another motivation, the second motivation which I will share of the larger research field is related to the following. The red blood cells which flow in our body, they have very large size, typically like 8 micrometer. And they are required to pass through capillaries which are only few micrometer, 3 micrometer or 4 micrometer in size. And how they do that is captured in this image, which is using a microfluidic channel. You can see this red blood cell has to change shape in order to do that. And this is actually very surprising because the membrane is not just a fluidic membrane. In fact, there is a cytoskeleton, which is a tethered membrane. And in a tethered membrane, you have a triangular lattice as shown here. You have nodes and you have connecting worm-like polymers. So this has to maintain the structure under different conditions. And what makes this problem special is that the cell is incompressible and the surface of the cytoskeleton is non-dilating. So someone compared this problem with the following, that you take a sheet of paper and you are asked to take this sheet and fold it up without cutting into a spherical shell. That's impossible, as everyone knows. And this is also similarly quite impossible, but it works. It's much more complex. What happened is that these ideas led to an explosion of theoretical work in this direction. They were inspired by the biomechanics of red blood cells, but you cannot test everything with red blood cells. So people thought, what are the other kind of membranes which will do the job? And that is where graphene related membranes came in picture, because this is a canonical membrane, a tethered crystalline membrane, where instead of the worm-like polymers, you have covalent bonds and a very neat honeycomb structure. What you have, one of the predictions I'll just mention, you have competition between deformation energy and entropy. And there are theoretical predictions that graphene should undergo a crumpling transition. And why these are grand challenges, the crumpling temperature predicted is 70,000 Kelvin. So no experimentalist is going to touch this, But then there are workarounds and some people are still trying. So this is one of the grand challenge in the broad field. Now I come to some of the related research I did in this area. And one question we looked at is, what are the configurations that a two-dimensional membrane takes on a corrugated substrate? So imagine you have put a graphene or any other two-dimensional membrane on a corrugated substrate. We may ask, will it follow the substrate as in the image on the right, or will it not follow the substrate as in the image on the left? And this depends on the energy cost of bending and stretching of the membrane, as well as the energy cost of adhesion. And so there is a competition between deformation energy and adhesion instead of deformation energy and entropy. Theoreticians like to write an equation such as this one, which describes the in-plane deformation, the bending energy, and a contact potential describing the adhesion. To look at this problem, we developed a four-dimensional lithography where imagine we put polymer resist, but this is not a usual resist. We can code this resist to swell in the Z direction, out of plane direction, and that swelling can cause the aspect ratio to increase substantially. So we begin with a resist which is small, and we could make it to increase by 10 times in height. And then we ask the question whether this graphene will follow the resist or will it not follow the resist. You can see here, when we expose this resist to a certain chemical, its height changes by a factor of 10, nearly factor of 10. So we have a strong control and a precisely controllable value of the aspect ratio. So what we did is we put these two-dimensional membranes on top of these pillars and studied how they get strained or they get delaminated. And there is a very beautiful theoretical prediction in this direction. People have considered this membrane attachment and detachment problem as a phase transition. And one can, for example, look at this phase diagram where height fluctuations versus the lateral length scale, which are characterizing the parameters, the geometrical parameters, and your membrane can be in an attached state or a detached state, depending on how much fluctuations you have over a certain length scale. So with these tunable lithography patterns, we could take the system from an attached to a detached configuration. And not only that, we could estimate the strength of the adhesive energy, which is the value we found, 2 milli-electron volt per angstrom square. This is one way, but there are many other ways in which mechanical instabilities can be brought in. The previous one is known as the snap-through instability. Here, if you take a sheet of polythene or any other thin film, you can stretch it in one direction, and that creates a quasi-periodic wrinkle array. And these are very difficult to solve in theory. They involve very difficult nonlinear partial differential equations. But there are very nice scaling laws developed by Sarda and Mahadevan. And from these scaling laws, we can understand what would be the wrinkle wavelength and wrinkle amplitude under a given condition of stretching. So for example, here there is a stretched polythene sheet, a very common object, and we have measured the wavelength as a function of some power of the strain, and it follows the universal scaling law. This kind of a stretching can also be experienced when systems undergo thermal expansion mismatch. For example, you put single layer CVD graphene on copper where it is grown and cooled down. You can generate, if you grow them on molten copper, you can generate extremely aligned wrinkles. And we looked at how this wrinkle morphology is important in the correct determination of the thermal expansion coefficient of this system. What does this universal scaling law say? It says that wrinkle patterns, whether you start from curtains or apple skins or human skin or polymer, they're all the same. The same law holds all the way down to graphene. But we did one interesting experiment. You take a multi-layer graphene oxide sample And if you stretch it in one direction, you get these wrinkle patterns, which are wrinkles are oriented following the universal scaling law. They are oriented along the strain direction. They keep reducing the width, and there comes a transition when the width is comparable to the wavelength of these wrinkles. So this is the width of the interconnect we made, about 10 micron or 5 micron. And then we see that the wrinkles get completely oriented in a different direction. And this very surprising result, where the universal scaling law does not seem to hold, has important implications. What it tells us is that if you make devices out of it, which are from bulk samples or 80 micron thick wide graphene, then you can get a reversible response if you change the resistance as a function of strain. But on the other hand, as you decrease the width of these interconnects, then the graphene cracks which form, they form along the entire length of the wrinkle, and therefore they tend to fold once it cracks, and the process becomes irreversible. So what we have shown is the wrinkle patterns determine the performance limits of graphene micro interconnects. Very important example where mechanical instabilities play an important role with reference to electrical transport. The last thing I will show is thermal transport. And unfortunately, we don't have any phonon meters. You can measure the electron transport easily by having an electrometer. Phonon transport has to be interpreted, and this experiment typically involves micro Raman spectroscopy. You use Raman both for heating a sample, as well as we measure the shift in the Raman modes. The shift in the Raman modes tells us the temperature. So the Raman is both the source, the heater, as well as the detector of the temperature. And by solving the heat diffusion equation, we can find the thermal conductivity of the system. For example, here we have graphene on a circular hole, and this is single layer graphene, which has extremely high thermal conductivity, 1200 watts per meter Kelvin. And this is measured using the Raman optothermal technique. If your film is sitting on a substrate, the things are a little more complex, because part of the heat goes through the substrate and part goes through the film. And so one has to perform more detailed experiments as well as simulations in order to arrive at the precise value of the thermal conductivity and the total interface conductance. One kind of sample that we looked at was graphene with rotational stacking faults and Moire patterns. So to illustrate what that means, a typical graphite sample will have the graphene layers stacked as AA layers or AB layers. That is one carbon atom right on top of the other, or one on top of the other, but shifted in a particular way, that is AB stacked. Now imagine if we rotate these layers in arbitrary manner, then you will get different angles, and you will get Moire patterns at certain angles. So what these samples have the tendency that they can support randomly oriented uniaxial wrinkles. And the reason is that you are having a system where there are crystallites with different orientations. And so the bending rigidity of this sample comes down, and system can support wrinkles. But the kind of wrinkles which happen here are very different. They are not quasi-periodic like we saw before. They are randomly oriented. And this is one such wrinkle. So we looked at thermal transport in these systems which have wrinkles and rotational stacking faults. And what we found is rotational stacking faults suppress the thermal conductivity due to scattering from additional phonon branches which form, and also due to zone folding. But once there are wrinkles, they tend to uncouple because they cause a spatial suspension of the film. So they uncouple the crystallites and actually cause an increase in the thermal conductivity. So in many different ways, I have shown that the membrane mechanics, the formation of wrinkles, mechanical instabilities is very crucial to towards the transport phenomena, electrical transport or thermal transport. And by itself, the mechanics of membranes is a very interesting topic. Before concluding, I'll just give a glimpse of other research areas where I work. One other topic I work on is the confinement of water and ions in sub-nanometer
So we
geometry.
are at 20 minutes now, okay?
Right.
Right.
Yes,
Yeah.
I'll conclude in a minute. So water and ions which are under sub-nanometer confinement, and yet another area of research is ultralight aerogels, such as the one you can see here, which is resting on a flower, and these are having ultra low thermal conductivity and good for space applications as thermal insulators. Also work on conducting polymers. Here is an example of a very nice breath analyzer we had made. I'll just conclude by thanking my current students and former students and postdocs, also our collaborators and funding agency. And thank you for your attention and look forward to questions.
A fantastic talk at the right time. And, well, let me ask you two questions rather.
Yes.
The first question is your transport that you talked about on graphene, the first problem with magnetic field.
Right.
Do you understand the origin of those resonances that you see currently? Right. And well, let me just ask that and then go further. Yeah.
Okay. So you are probably referring to the pseudomagnetic field, right?
Yes.
So in case of pseudomagnetic field, it is very well theoretically understood. There are no doubts about it. When you create a certain non-uniform strain field, just a simple stretch will not do. That non-uniform strain field is equivalent to putting a vector potential in the Hamiltonian. So one can show that equivalence. And that's why fields which are impossible in the lab, 600 Tesla, but pseudo fields, not real fields. So this only the carriers feel them, we cannot feel them. Right? And so these can be created, and they are understood and verified by scanning tunneling spectroscopy on random locations, not controllable.
But the structures on that.
Right. Let me go to that.
Yeah.
Right. So which of these are you referring to? Any structure here?
Yeah. So let's take the spectroscopy.
Right.
Let's go to the previous thing.
All right.
Let's say the previous thing where you have now structures, right?
Right.
On your resistance.
Yes. So where suppose you have a real magnetic field, then you will have the electrons going in cyclotron orbits and you have confinement. So the density of states will get quantized and you will have Landau levels.
Yeah.
So at the position of as the Fermi level goes through different Landau levels, you are going to get these peaks.
Yeah.
This is what you get with real magnetic field. And so we understand whatever we understand for a real magnetic field applies here, except that the field is pseudo in nature.
So the periodicity here refers to what periodicity?
So this gate voltage refers to the amount of carriers you are adding to the system. This is like carrier density. So I'm changing the Fermi level, and the Landau levels are going to appear at certain value for a fixed magnetic field at certain carrier densities. I'm going to cross the Landau level. If I add certain number of carriers, I will cross one Landau level. If I add more, I'll cross another Landau level. So the difference between two Landau levels is fixed by the magnetic field, which could be several Teslas of magnetic field.
So this would be manifested in a single layer graphene far better than multi-layers, or is this related to the kind of the rotational disorder in layers?
No, this is just simple single layer graphene. You will also get it in bilayer graphene or something.
Let me take it to the next question. You presented some giant or grand challenges in the field.
Yes, this was one of them. We can't control the mechanics of the membrane. We can't create membrane structures with desired shape or curvature. That is a grand challenge.
I see several grand challenges, and those
there are only two.
That, no, I'm saying that what you present are interesting, important to be pursued. But let me ask you the limitations in pursuing grand challenges, what you see as the limitations in our context.
Right.
Or you don't see any limitation at all, or you see significant limitations.
Some different ideas might be able to bridge the gap. So conventional way of doing things is not going to work. So this can be realized. For example, I talked about the other grand challenge, where there is a crumpling transition at 70,000 Kelvin. So how do you bring that down depends on, can you create a new membrane whose bending rigidity is much lower? Need not be graphene. I just took graphene as a prototypical. So chemist can synthesize a membrane with very small bending rigidity, and maybe this comes down to 1,000 Kelvin. And there is a wealth of literature, decades of research, which is waiting to be verified. It might have implications on what we understand about red blood cells also.
So, I'm looking at it for the past 25, 27 years of my life here at IIT Madras.
Mm-hmm.
When you looked at grand challenges of these kinds in an experimental context, there are many barriers that I see.
Right.
So in the kind of two challenges that you presented,
Mm-hmm.
they are today, what comes out from you is that they are idea challenges. I mean, challenges limited by ideas or limited by our inability to overcome them, not
Right.
limitations in the structure or our resources or infrastructure.
Right. Yeah. Cutting edge technology certainly helps. There might be new technologies which come which help to realize certain ways of manipulating membranes. For example, the graphene kirigami came only a few years back. Someone had the idea that you can cut it up and do wonderful things with it.
Yeah.
Right. So technology is one, and then there could be some different ways of doing the same thing rather than trying it out in the same way. So as you rightly said, that ideas are the key thing. Can somebody make a membrane which is possessing these properties but is different from graphene? Everyone tries graphene. Why don't we try something else?
Sure. Thank you. Let us go on to Madhav Ranganathan.
Yes, am I audible?
Yes, please.
Okay, yeah. So I had a question regarding the instability in the film. You said you stretch it in one direction and you get these wrinkles, right? Now,
right. Shall I go to that slide? That would be good.
Yeah, sure. Just a plain membrane without any substrate, right?
Okay.
Yeah. So I think somewhere you had a length scale of this wrinkles coming in, okay? And
Right.
you said the length scale, it should go as the bending modulus should be involved, and also there should be some shear modulus. The graphene sheet has a shear modulus.
Graphene's bending rigidity. You're asking where does it come in this? So
No,
in this,
so yeah, this gives the length scale of the wrinkling, right?
Right. This lambda is the wavelength and thickness and lateral length scale and the strain you have applied.
So what is this lateral length scale?
So this is some lateral dimension. No? Samples also have a. So you are clamping the membrane. So there is a.
Right.
It's not completely a freestanding membrane. The ends are clamped, and actually the ends experience biaxial strain. In somewhere in the center, you have uniaxial strain. So this refers to the wrinkling in the central region, and there is a length scale involved with reference to how far your clamps are.
Okay, and are you applying some force on the clamps, or
yes, with a force? Only with the force you can stretch this, right?
So that force doesn't come in the length scale, or
so in this scaling relation only has these quantities. So that's why it's like a universal scaling relation. Force doesn't appear in that the magnitude of the force.
But the strain appears, right? Epsilon is a strain.
Yes, the strain appears.
Okay. So the strain was probably related to the force.
Right. I would refer to this paper, which is the most best paper on this topic, Sarda and Mahadevan, and they have discussed in very nice manner.
But usually in all these length scales, there is usually some modulus of the material that appears.
Okay.
Like usually it is bending to shear, or some such thing that causes.
Right. There are like competing effects, and then what the scaling laws are originating from two competing effects. So there are different conditions under which these scaling laws are derived. One is for a freestanding film, another is for a film on a substrate, and the laws are slightly different for each case.
Okay. Yeah. Thank you.
Somya Dutta?
Hi.
Hi, Shom.
Hi. Yeah, Manu. Yeah, it's a nice talk. So I have a very specific question. So one thing is, you mentioned like something like 4-dimensional lithography, something like that. What does it mean actually?
Right. I'll just go to that. Yeah, 4-dimensional lithography is just a word I have coined, so you won't
that's
find it anywhere. What it refers to is, in lithography we make 2-dimensional structures, and if you decide that height is also a variable, you can make 3-dimensional structures.
Yes.
But here it goes beyond that, in the sense you have a 3-dimensional structure, well-defined height and aspect ratio, everything. But by exposing to a particular chemical, then you can create a different aspect ratio. So it can swell, and the swelling is not random. As you can see, the swelling ratio is controlled with the electron beam dose. So I can say I will make the pillar go from this height to another height. So it's an extra dimension added to what you can do beyond 3 dimensions.
And another question, maybe I don't know how relevant it is. So for example, you are using this graphene or even RGO, right? So
Right.
Is there? I mean, have you come across about this this gauge factor or those numbers?
Yes, gauge factor. No, if you use it as a
Yes.
strain sensor,
Uh-huh.
if I go to this slide where the source of increase of resistance is the formation of cracks, but these cracks don't penetrate. So there is always a finite amount of resistance which is present despite the cracking. And so the gauge factor goes about few hundreds. Right.
Okay. 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 Thank you.
Let's go to Ranjit, and that's end of it. We are already at 6:33.
Manu, I have a small question, rather query.
Yes,
That
Ranjit.
in this graph in the Landau level that you talked about, so the carrier densities are appearing due to what kind of impurities you have or some defects?
I mean, this is the usual thing, right? You change the Fermi level, there are no impurities. Of course, system has disorder and impurities. You are tuning the Fermi level by applying the gate bias, right? So when you apply the gate bias, you can move the Fermi level into the conduction band or the valence band.
No. So the thing is that generally we won't see Landau level until unless there are some kind of impurities kicks in.
So there is always some amount of disorder always present in the system. All these kind of systems, such as the one here shown by Novoselov, which is the first report on quantum Hall effect. You vary the carrier density, which is gate voltage, and then you get these oscillations. The system has a finite amount of disorder, and then you have these edge currents.
I see. Because there are some curious papers like creating vacancies, mono vacancy, di vacancy. Then you can create new kind of Landau quantization. It can be square root of n, it can be n square like that.
Oh, okay. That is very interesting. So maybe we could discuss that. I'm not aware of these papers that it is, but in these samples, no specific defect was created.
Okay. Yeah, I'm done.
Right, Manu. Very nice. Let's move on. Aarti.
I'll just.
Aarti, are you there?
Yeah, I'm there. I'm very much here.
Yeah,
you can share screen.
Yeah, absolutely. We are at 6:35.
Yeah, sure. Okay, so am I audible?
You're audible. The screen has not come yet. Your screen.
Am I audible?
Yeah,
I hope I am.
You're audible.
Okay. My connection is a bit unstable, so I just like to warn you beforehand. So thank you for giving me the opportunity to present my work. So the title of my talk is Transients Generate Memory and Break Hyperbolicity in Stochastic Enzymatic Networks. And here is the outline. I'll first give a very brief introduction to classical enzyme kinetics based on deterministic networks, and then recent experiments on single enzyme kinetics based on stochastic networks. I'll then present a generalized theoretical formalism that unifies the results of deterministic and stochastic networks within a single framework, followed by comparison with experimental data, new theoretical predictions, applications, future work, and possible collaborations. So enzymes are molecular machines that speed up the conversion of substrate into products without getting consumed in the process. the question of fundamental importance in enzyme kinetics is what is the rate of product formation, or what is enzyme velocity? So answer for this was first provided by Michaelis and Mendin in 1913 for a deterministic network of 3 elementary reaction steps. In this mechanism called the Michaelis-Mendin mechanism, enzyme reacts with a substrate to form an enzyme-substrate complex, which can either dissociate to form an enzyme and substrate or form a product while regenerating the same enzyme. So the steady state velocity for this mechanism was derived by Michaelis and Mendin, and it is called the classical Michaelis-Mendin equation. So this happens to be one of the most celebrated expression in biochemistry, as it provides a fundamental hyperbolic relation between enzyme velocity and substrate concentration. It is derived using deterministic rate equations for the time evolution of enzymes, enzyme substrate, and product. And this implicitly assumes that enzyme concentration is thermodynamically large. And this means that we are in n going to infinity limit, where n is the number of enzymes. And this derivation further assumes a timescale separation in which the equilibrium between enzyme and enzyme substrate is established faster than the product is formed. So the hyperbolic dependence of velocity on substrate concentration results in a linear relation between the reciprocal of velocity and reciprocal of substrate concentration. And kinetic data for vast majority of enzymatic reactions, when fitted to this linear form, yields rate parameters of the Michaelis-Mendin mechanism. And these are the rate parameters that we can obtain from this linear fitting. So the hyperbolic dependence of enzyme velocity on substrate concentration is seen in many different areas of chemistry and biology, including surface adsorption, bulk enzyme catalysis, single molecule catalysis, transcription, translation, kinetics of linear motors, rotary motors, chromatin remodeling, so on and so forth. So under physiological conditions, however, enzyme concentrations are not thermodynamically large. Typically tens to thousands of enzymes catalyze thousands to millions of substrates. So the question of relevance is the Michaelis-Mendin equation a valid description at such low enzyme concentrations? So to answer this, we need to understand a few facts about enzyme kinetics at the molecular level. First, that enzymatic reactions at the molecular level do not proceed deterministically. Fluctuations of both quantum mechanical and thermal origin, together termed as molecular noise, are inherent to reactions catalyzed by individual enzymes. And because of these fluctuations, each step of the Michaelis-Mendin mechanism I just showed is stochastic, implying that neither the lifetime of a given state and nor the state to which it transits can be known with certainty. And the effect of these fluctuations, and thus the uncertainty, diminishes progressively with the increasing number of enzymes and vanish for their bulk amounts. And the limit of n going to infinity, the classical rate equations are recovered. So this is the classical limit. And away from this limit, fluctuations are important. In this limit, fluctuations are not important. So n going to infinity is the limit in which fluctuations are not important. Away from this limit, fluctuations become important, implying that we need to account for stochastic effects. So what is the difference between classical and stochastic enzyme kinetics? In classical enzyme kinetics, products are formed together in bulk, and one can define product concentration and one can define the rate of change. In stochastic enzyme kinetics or kinetics at the single molecule level, products are formed one by one in discrete integer jumps. One cannot define product concentration and one cannot define their rate of change. So instead, the kinetics is described in terms of 3 time scales: the lifetime of enzyme and enzyme substrate states, waiting time between two consecutive products labeled as tau1, tau2, tau3, and tau-p, and turnover time for the pth product labeled as capital T1, capital T2, capital TP, TP, start time t equals to 0. Okay, So here P is the turnover number for the pH product formation or pH enzyme turnover because they're coupled. Okay, so it turns out that all these three time scales are stochastic quantities with well-defined distributions, and the enzyme kinetics at the level is thus defined in terms of distribution of waiting times or turnover times. And the hierarchy of distribution depending on the distribution depends on 1 time, 2 times, 3 times. And this is called, say, 1-point distribution, point distribution, and 3-point distribution. And the first moment of this distribution is the mean waiting time. The variance of distribution is called Wayperson. Distribution is waiting time quotient.
Arthi,
So
if you
these
can
are
go,
the
go
measure, the
2
distribution
minutes
and
back
correlate,
and then
and this
speak.
variance is a measure of fluctuation. This is a measure of mean. It measures.
Her connection is bad. Arthi has gone away.
She has logged out.
I'm back.
Oh yeah.
Please go
It
2
is.
minutes back and
Yeah,
then
I just go. I just. So where is my presentation? Okay, so 2 slides back.
yeah, this is fine.
This is fine. So repeat.
Yeah.
Yeah. Okay. So what is the difference between classical deterministic and stochastic enzyme kinetics? In classical enzyme kinetics, products are formed together in bulk, and we can define product concentration and their rate of change. In stochastic enzyme kinetics, products are formed one by one in discrete integer jumps as shown here. So we can't define concentration, product concentration, and the rate of change. Instead, the kinetics is described in terms of 3 time scales: lifetime of E and ES states, varying time between 2 consecutive product formation, okay, which is labeled as tau1 for the first product formation, tau2 for the product formation between second product and first product, and so on. Okay. And then we have turnover time, which is TP, and this is the turnover time for the pth product formation. So here P is the turnover number for pth product formation or pth enzyme turnover. So these are coupled. So if I say pth product formation, it means that P enzyme turnovers have happened. Okay, so this is related because they're coupled to each other. So whenever there's product formation, the enzyme turns over. So it just turns out that these time scales are stochastic quantities with a distribution. So the kinetics at the molecular level is described in terms of the distribution of either waiting times or turnover times and their moments. So as I said, there's a hierarchy of distribution, depending on whether this distribution depends on 1 time, 2 times, or 3 times, and so on. So this is 1-point distribution, 2-point distribution, 3-point distribution, and the mean of this is mean waiting time. The variance of this is waiting time dispersion. The first moment of this is waiting time correlation, and so on and so forth. So all these distributions, correlations, and variance, they are measure of fluctuations. This is a measure of mean. So in classical enzyme kinetics, we only know this. At the molecular level, we can in principle calculate this. And this is what we have done in a formalism. We provide a general theoretical framework to calculate all these kinetic measures of interest. And the quantities which are listed inside the box have been measured in a landmark experiment, which 2006. Okay, so in this experiment, the turnover kinetics of the single enzyme of beta galactosidase was measured using fluorescence microscopy. So here substrates were non-fluorescent and products were fluorescent. Okay, and the waiting time between 2 product bursts was found to be stochastic quantity with a distribution which is shown here. So the waiting time between two consecutive product bursts when recorded repeatedly under identical condition yielded a distribution of waiting time which is given here, which is shown here. So this is waiting time distribution that was obtained. So it's to be noted that beta-galactosidase, the enzyme that was used, has 4 binding sites, 4 independent and identical binding sites, and it is known to follow the Michaelis-Menten equation in bulk. At the single molecule level, however, the inverse of the first moment of the distribution showed deviation from the Michaelis-Menten equation, implying that the Michaelis-Menten equation is not obeyed at the molecular level. So this was again the measure of mean. The measure of fluctuations included of the distribution called randomness parameter, 2-point waiting time distribution, 2-point waiting time correlation, and this was found to be greater than 1, which is a signature of dynamic disorder. I'll not have time to get into this, what is dynamic disorder, but this found to be greater than 1, which is a signature of dynamic disorder. So this showed long first waiting time is likely to be followed by long second waiting time. And this is a signature of positive molecular memory. This showed that waiting time correlations were positive, implying that turnover times are statistically dependent. So, so the question of fundamental relevance is, how can molecular memory shown here? How can molecular memory shown here and statistical dependence between consecutive turnover events emerge from the fundamental memoryless character of elementary reaction steps in mass action kinetics? Okay, so to answer this, we provided a generalized theoretical framework that unifies the results of deterministic and stochastic enzyme kinetics within a single framework. So this framework was provided by the chemical master equation approach of stochastic processes. So chemical master equation is written for the time evolution of the number of species in a mechanism at a given time. And it accounts for stochasticity in each step of the mechanism in terms of its transition probability, which is shown here on the same color as the step. Okay. So in the limit of n going to infinity, which is a classical limit or the thermodynamic limit, we recovered the classical rate equation, classical deterministic rate equations. And this was shown by Bartolome in 1962. So the solution of the CME yields the distribution of the number of products at a given time. And this belongs to the count process description of stochastic processes. And this is relevant for large number of reactants and products. What is relevant for single enzyme kinetics is the distribution of waiting time or turnover time. And this belongs to point process description. So the question is how to go from here to here. So a few years back, we solved this chemical master equation exactly for the first time to present or to propose a novel time-based approach to obtain turnover time distribution for any n and p, where n is the number of enzymes and p is the turnover number. And skipping the detail is just required using generating function method relation between counting and point process to obtain exact turnover time distribution from CME. So waiting time distributions and correlations were obtained from the Gillespie simulations, and together they provided the experimentally relevant quantities. So I'll just show the results now. What we found is that for n equals to 1, the distribution, the waiting time distribution was independent of the turnover number, and the inverse of the mean waiting time exactly recovered the Michaelis-Menten equation. This is single enzyme velocity. This is classical enzyme velocity. And together they provided the single enzyme analog of the classical Michaelis-Menten equation. Okay, so this is point process description, this is count process description, and we have just equated the two to give single enzyme analog of the classical Michaelis-Menten equation. Again, this is a measure of mean. The measure of fluctuation included randomness parameter, which was found to be less than 1, and waiting time correlation, which were absent. Now, this implies randomness parameter less than 1 implies that there is no dynamic disorder. And this is always true for a linear network, such as the Michaelis-Menten network. And there is no correlation means that there is no molecular memory. So this is for n equals to 1. For more than 1, we found that the waiting time distribution depend on turnover number for lower turnover numbers, but become independent of it at high turnover numbers. From this, we found that for turnover number less than P star, the Michaelis-Menten equation is not obeyed. For turnover number greater than P star, the Michaelis-Menten equation is exactly recovered. So we call this the transient regime and call this the steady state regime. The question is, what is P star? So we showed that P star is the critical turnover number beyond which the waiting time correlations are absent or become 0. So in the transient regime, turnover times are correlated. Timescale separation, which was used by Michaelis and Menten to derive Michaelis-Menten equation, is not valid, and Michaelis-Menten equation is not obeyed. In the steady state regime, turnover times become uncorrelated, timescale separation is valid, and Michaelis-Menten equation is exactly recovered. Stochastic network or stochastic kinetics, however, with negative or no memory and no dynamic disorder, does not recover experimental results. So we conclude or we infer that single enzyme Michaelis-Menten kinetics cannot recover experimental results. And we need to include two important aspects of enzyme kinetics at the molecular level. First, that an enzyme can change its conformation during the course of a product turnover cycle. And second, that most enzymes have multiple binding sites. Beta-galactosidase, for example, has 4 binding sites. So we included this in a parallel pathway Michaelis-Menten network, calling it PPMM network. And in its minimal form, it has an enzyme which can fluctuate between 2 conformation states before forming a product through either one of the 2 possible pathways. And in the absence of these conformational fluctuations, we recover the Michaelis-Menten network. So this is a model for single enzyme with single site. For multiple site, we consider n replicas of single enzyme network. For beta-galactosidase, we consider 4 replicas of single enzyme network. So we solved chemical mass equation for single site and multiple site models and compared our results with experimental data. So we found that both single site model and multiple site model reproduce the mean and variance of the distribution, mean and variance of the waiting time distribution quantitatively. But the single site model does not yield memory and therefore cannot rationalize experimental data. Multiple site model with 4 replicas can recover mean and variance of the distribution as well as positive correlations and positive memory in excellent quantitative agreement with single enzyme data. So this is a summary where we show that only parallel pathway Michaelis-Menten mechanism with 4 binding sites can recover all the experimental results, including positive memory, positive correlations, and dynamic disorder. Single site.
20 minutes now, okay?
Okay. Single site model, irrespective of the mechanism topology, cannot recover experimental results. So the question, what is the source of memory in multiple site model? For this, we carried out detailed theoretical study. And we found that, in the presence of multiple sites, there emerges a new time scale called recurrence time. Okay, and this makes the pth waiting time dependent, conditionally dependent on p minus 1th turnover time. Okay, so this conditional dependence is absent for a single enzyme, therefore it has no memory, but it's present for multiple enzymes and it has memory in the transient regime. So the next question is, what is the duration of this transient? To quantify this, we introduce new statistical measures to demarcate transient and steady state regime in single enzyme kinetics. And earlier known measures for single site catalysis were proposed in the context of molecular motors. We generalized them to multi-site catalysis And using this, show that for single site catalysis, these two measures are always equal. Measure of number and temporal fluctuation always equal for single site catalysis, but for multi-site catalysis, they are unequal in the transient regime, but become equal in the steady state regime. And this equality is attained at P star, which determines the duration of this transient. Okay, so in summary, what we have done is we have generalized the Michaelis-Menten formalism to all n time, and n is the number of enzymes. So this is what we have known so far, that in the classical limit, transient regime is too short to be observed, too short to be observed, and Michaelis-Menten equation is obeyed. What we find is that for n equals to 1, transient regime is absent, and Michaelis-Menten equation is obeyed, therefore. For n greater than 1, on the other hand, there emerges a non-classical transient regime in which turnover times are correlated and Michaelis-Menten equation is not obeyed. And the steady state turnover times become uncorrelated and Michaelis-Menten equation is obeyed. So from this, we conclude that single molecule experiments on beta galactosidase capture the results of the transient regime. Okay, so the emergence of molecular memory in an ideal enzyme with non-interacting binding sites can be viewed as a null model. And for this null model, we predict that the Michaelis-Menten equation will be violated in the transient regime, but will be obeyed in the steady state regime. And on the basis of this, we expect that in a real allosteric enzyme with interaction between binding sites, the Michaelis-Menten equation will be violated both in the transient and steady state regime because of the presence of molecular memory. So this analysis holds the promise of theoretically understanding the phenomena of enzyme cooperativity at the single molecule level. So the generality of our analysis for number and temporal fluctuations for processes at molecular scale has practical applications in different areas of physical, chemical, and biological sciences. And this include mesoscopic quantum transport, including the short noise in electronic circuits, simulation statistics of an ensemble of quantum dots, single molecule photon statistic, single nanoparticle catalysis, stochastic modeling of single enzyme cooperativity, drug delivery based on enzyme inhibition network, the search for non-stationary phases in molecular motors, and finally, it also invites the application of Bayesian probability to machine from turnover time data. So this work was mainly done with my PhD students, and a part of this work was done at DAMT Cambridge. And thank you for your attention. I hope I am well with it.
Sure. So obviously, the generality in all of these subject areas that you mentioned, that would take the stochastic model to wider acceptability over a range of phenomena. Now, there are a lot of single particle, nanoparticle catalysis experiments. There are mass spectrometric experiments. There are protein, you talked about enzymes, but then polymer related studies. So are there some examples wherein similar models can be explained, or it is data are scarce in those areas?
You see, why I have included these examples, I mean, these are the examples where we can actually use the formalism, because the formalism is very general. So the formalism generality comes from the fact that we have solved it for a problem in which we have an enzyme with non-interacting binding sites. So if you have, photons, for example, which are non-interacting, you can use the formalism, because we have formalism is that these are how, the relation between number and temporal fluctuations is going to be. So it is general to that extent. So these are generically studied, I mean, without any, this thing of any chemistry. So it's not that nanoparticles will behave any differently. As long as nanoparticles have non-interacting binding sites, they will also follow what I've discussed. But if nanoparticles have this allosteric effect, in that case, we have to modify the model. So it is general to that extent. So it's true for all, enzyme catalyzed reaction, for example. You can take. Yeah.
Are there some specific cases where, so let's say there are people who study in a single aluminum cluster of 7 or 8 atoms, you do reactions in a mass spectrometer. Are there some data of this kind exist? So I'm wondering whether any of those experimental data could be put into these equations and get some newer insights in those processes. You say that it can be applied, but are there
No, so so the only difference that we have to know, if you have an enzyme or you have even a nanoparticle in which there are many sites, whether they interact or not. So if they, so this model is for those sites which don't interact. If they interact, then we have to modify the model. So at the level of theory, this is the basic difference. I mean, it doesn't matter what the chemical detail is, this is going to be true. So that where the chemical detail is going to come in is in the rate parameters. So when we fit our theory with data, rate parameters will be different for different nanoparticles, for example. Okay,
well,
so
I have
this is general. This is general.
Okay.
Sorry, yeah, please.
I have some a case wherein we have looked at some new kinetic models in nanoparticle reactions, and something is under review in JAX, and I will come back to you with some of these.
Yeah, sure.
Are there other questions, colleagues?
I think Madhav has some questions.
Yes. Okay, go ahead. Madhav, I see.
Yeah, can you hear? Can you hear me?
Yeah.
Okay, so the n equal to 1 case. So there you said you get Michaelis-Menten.
N equals to 1 case, we get Michaelis-Menten. Yes.
Right. And so is there some underlying, I mean, are you assuming that you form the enzyme substrate or anything?
No. So the assumption is as much as what Michaelis-Menten assumed, that this is pseudo first order reaction, where substrates are not acting. But here, so this coming from the fact that Michaelis-Menten equation is obeyed because something which I didn't explain is that that single enzyme network have fermionic character. Okay, so an enzyme can either be in E state or ES. Okay, and because of that, what happens is that these waiting times are always independent. And because of that, there is no memory, and whenever there is no memory, we'll recover the Michaelis-Menten equation. So it originates from the fact that these waiting time distributions are independent, and therefore we can recover the Michaelis-Menten equation. Whenever there is dependence, the Michaelis-Menten equation is not recovered. So that is what hyperbolicity is coming from, when Michaelis-Menten equation is, sorry, I mean, when memory is there, Michaelis-Menten equation is not obeyed. When there's no memory, Michaelis-Menten equation is obeyed.
But suppose you take some other kinetic process and you examine it at the single particle level.
Say it again, Madhav. I didn't.
Yeah, suppose I take some other kinetic process. Okay, like what Pradeep had said, you take some reaction on an particle or any chemical reaction at a single particle level. Okay, you will get.
Okay. Yeah, so it's for enzyme kinetics, because what is different about enzyme kinetics is what I explained is that there's a turnover. So enzyme turns over. It doesn't, get, it doesn't react in the reaction. So every time there's a reaction, there's enzyme turning over all the time. So whatever this analysis is, it is for enzyme turnover. So therefore, it is for catalytic reactions. So whether nanoparticle or anything, and it's also true for even whatever I've showed you here, because all these have the same feature. Whatever examples have been shown here is true where it can be applied directly in biological systems. So.
Okay, thank you.
Okay, yeah. So any other question?
I have one question, Hemchandra.
Yeah.
So, Professor Aarti,
One quick question is like, so when these single molecule kinetics deviate from the traditional Michaelis-Menten fitting, one thing that we as experimentalists try to consider is the enzyme fatigueness. In the sense, like when you perform the same experiment on the enzymes multiple times, so it tends to deviate from what we generally observe in your bulk studies. So is there a theoretical understanding to consider this enzyme fatigueness in the sense, like, because you also mentioned that, you know, there is some molecular memory with this, with the enzymes involved. So if you perform the same experiment on the same enzyme, not different enzymes multiple times, but on the same enzyme repeatedly, the enzyme fatigueness occurs, and then it starts deviating from the traditional Michaelis-Menten kinetics. So is there a theoretical understanding for this?
So I don't know what you mean by fatigueness, because I really don't know. What I know that we can actually distinguish whether this, this effect is originating from the fact because of inherent, fluctuations because of which memory is appearing, or there are other reasons. So at the present in the model, there is no other way we can get memory. In fact, there's nothing. Okay, so we are just taking the same formalism of Michaelis-Menten and showing that there will be memory. Okay, so we have not done anything. So if we put anything extra, there we're going to see some other effects which are not included. So if you tell me like what those effects are, it can be included in principle. Okay, so at the moment, it is at the level of what Michaelis-Menten had done for classical enzyme kinetics is what we have done for stochastic enzyme kinetics when there are fluctuations. So formalism is for all n, like, n time, which is what I said in n that we have generalized it to all n. So now if you say that for a specific case, this is where what we are seeing, then we have to look back into the model whether we need to, add something more to it. Okay.
All right, let us move on then. Next, we have Rajneesh.
Yeah, I will start sharing my screen.
It is 7:08, Rajneesh.
Yeah, I'll try to be on time. Okay, is it visible to everyone?
Yeah, we can see that and we can hear it.
So, good evening, everyone. So today, the presentation which I have today, or the discussion which we are going to do today, I would basically show you some experiments which we have done with hydrates. I'll try to give a small background about hydrates, and then see if the interesting whatever information we see, whether I can get some extra information from all of you, because many of you would be working on nucleation and growth of hydrates from different domains. So it would be interesting for me to understand from your perspective how some of these could be explained. So the hydrates which we typically work on is gas hydrates. So basically gas and liquid is brought in contact with each other. And the major challenge as a chemical engineering point of view, what we see is that there is going to be a severe mass transfer limitation, and being exothermic process, there will also be heat transfer limitation. So in this particular slide which you see, we have, okay, let me go to the pointer option. So we have a reactor which is basically half filled with gas and remaining half is filled with water. And then we try to stir it so that there is a good contact between this gas and the water. And at certain temperature and pressure conditions, which you see over here, which is above 0 degree, you will see that this water will get converted into solid hydrate. So this is right now, you see this is the interface. Below this you have liquid, above this you have gas. And this is a 0 second, that is basically, this is the time when the hydrate would nucleate. And then what you see here will be mostly the growth phase actually. So you see in a matter of seconds, you will see that this water has got converted into hydrate, which is very much similar to ice. There is no much of a difference. If you really, physically, there is no difference at all, unless until you do a spectroscopic analysis of the solid hydrate phase. So, so basically, it's quite easy for you to synthesize these hydrates in lab. What we can see though is that the typically hydrate, what basically you see that there is maximum concentration of gas and liquid at the interface. So, and also the stainless steel wall, which basically the reactor is made up of, is slightly cooler compared to the bulk liquid. So this is where you will see on the interface, you will see somewhere the hydrate would nucleate. And this is expected, and it would start growing basically under the interface in the bulk liquid phase actually. going into looking at this hydrate at molecular level, I like to show these slides. Basically, depending upon the size of the guest molecule, hydrates basically form different kind of structures. If you have a gas like methane, which is basically mostly we use, because I will explain that in the next slide. Methane is of such a size that it occupies the there are two different type of cages in structure 1 hydrate. There is 2 small cages, 6 large cages, and these cages are made up of hydrogen bonded water molecule. There are 46 water molecule in 1 unit cell structure actually. So the case of this large cage is made up of 12 pentagonal faces and 2 hexagonal faces, whereas the small cage in structure 1 is made up of 12 pentagonal faces. So if you see here, you see that because there are only 12 pentagonal faces, the radius of this particular cage is like slightly smaller compared to this cage, which has on the top and the bottom 2 hexagon faces. So it's slightly bigger. So if you form hydrate with methane, which is of such a size that it likes to go into the large cages as well as the small cages. So even if you get a sample from under the earth, which is there for millions of years, you know that these hydrates around all the 100% of the large cages will be filled by methane, and around 90% of the small cages will be filled by methane. But if you have a gas molecule which is slightly bigger than methane, say for example carbon dioxide, it also forms a structure 1 hydrate, but if you form it in lab for many years also, you would see that all the 100% of the large cages are filled with carbon dioxide, but only around 60 to 70% of the small cages basically goes into the small cages. And one of the reason could be that CO2 is slightly bigger in size and it's a little difficult for it to diffuse into the small cages. If you have a larger molecule than carbon dioxide like propane, then propane is too big for even the largest cage of a structure 1 hydrate, and this is when this hydrate structure will change to structure 2. So you see there are 4 hexagon faces over here, and this cage is slightly bigger in size compared to what you see in a structure 1 actually. The small cage is still the same. So large molecule like propane goes into the large cages, and all the small cages will remain empty. Nothing will go into the small cages, and still this hydrate will be stable. And this is in fact stable at much lower pressure at any given temperature compared to what you would see in pure methane hydrate of a structure 1 hydrate. So large cages gets occupied with larger molecule, and the small cages remains empty. That is a structure 2. But if you have a molecule which is smaller than methane, it also forms a structure 2 hydrate. And the reason is that there are 16 small cages in structure 2 hydrate and only 8 large cages. So there is more probability for this small molecule to find themselves in a small case. They get more comfortable over here. And I just wanted to explain you that there is no chemical reaction happening between the gas and the water. Water is bonded there by hydrogen bonding, and the gas is intact over there just by van der Waals interaction. There is no chemical reactions happening over here. So most of the gas which forms hydrate are basically non-polar. There are some polar molecules as well, but mostly non-polar gases basically forms hydrate very easily. So in a structure 2 hydrate, you have 16 small cases, 8 large cases, and these are made up of 136 water molecule. And similarly, if you have even larger molecule than propane, pentane, go to neohexane or something like that, then that large molecule cannot fit into this, so they form a different structure. Now in this case though, there is no possibility of this large molecule to stabilize this hydrate alone. So you need a help gas like methane or nitrogen. Something has to go in these small cages, and this is when this hydrate becomes really stable. So what you see here, that if you have 1 meter cube of this hydrate, you basically store a large amount of gas in this hydrate. 1 meter cube of this hydrate will have around 170 meter cube of gas at a standard temperature and pressure conditions. So looking into this configuration, now you know that this could be a very good storage material for gases. This could also be a very good material for separating gases of 2 different sides. So if you have a carbon dioxide and hydrogen, or you have a carbon dioxide or nitrogen, you should be able to basically preferentially form one type of hydrate, and that hydrate will only go into a particular cage, and you should be able to basically separate this gas mixture. So these are basically, this presents some of the interesting application for gas hydrate based work. So the unit cell structure looks like this. This is structure 1 hydrate, this is structure 2 hydrate, and you have this hexagonal structure H hydrate. And there are many other structures, but typically with the temperature and pressure conditions which you can attain very easily in the lab, these are the structures you typically form. So, but why one should study gas hydrate? So we typically do a lot of work. Most of our funding come from this because in India, we have a huge resource of methane hydrate under the seabed.
So a lot of funding comes to our lab from this, where they want, this is completely applied research, where they want us to develop processes to recover methane from under the seabed. Now, under the seabed, why hydrate forms? Because hydrate typically forms at high pressure and low temperature, and under the seabed, you have basically both the conditions met. You also have water, and you also have the biogenic origin or thermogenic origin of gas. So all the components to form hydrate is present under the seabed, and this is why millions of years we have huge amount of methane under the seabed. In fact, the amount of methane which you have under the seabed in hydrate forms basically is twice as much as all the fossil fuels put together. So this is an area where we are contributing a lot. But then other than that, we also use as a means to hydrate as a means to develop technology. So it could be used as gas storage for hydrogen, for natural gas. It could be used to separate gases of carbon dioxide and methane, or carbon dioxide and hydrogen. It could be used for desalination because you have a water soluble component in there and you want just the water to form hydrate. So whatever other components you have will just remain in the mother liquor, and water will get converted into hydrate, and you should be able to dissociate that hydrate to produce fresh water. Then you can use this because there are a huge amount of hydrogen bonding involved over here. So there is a lot of delta H involved when there is a phase transition. So you can use it for refrigeration purpose actually. So it also acts as a phase transforming material. If you have CO2 hydrate, you can basically have a fire extinguisher. As I was telling you, there is huge amount of CO2 you have in there. You also have water. So fire extinguisher could be one application of hydrate. And then there is flow assurance, which is how basically hydrate came into, basically people started working on it. Because during 1960s and 17, when a lot of oil wells were being dug deep down under the seabed, they started seeing that the oil and gas pipelines basically gets plugged. And this is when all the research basically started. Initially, they thought it was ice, but ultimately they figured out that these are hydrates, which can form even at 20 degrees centigrade. So what we typically do in our lab, being an applied research, we are looking into enhancing or altering the rate of hydrate growth. In flow assurance, like in the case of oil and gas pipeline, you need to identify inhibitors, which basically would inhibit hydrate nucleation or basically delay the growth of hydrate or agglomeration of hydrate, so that you can basically use those inhibitors to maintain the flow assurance in a pipeline. Or when you're trying to recover methane from under the seabed, you basically need an additive which would somehow enhance the rate of dissociation of hydrate, so that within a shorter period of time, you can recover more amount of methane, because industry would be interested in investing or giving lesser energy to produce a lot more methane out of it. In most of the technological advancement which we talked about over here, hydrogen storage or gas separation, you're basically you need to form a lot of hydrate, and this is when you need a lot of promoters which can basically promote the hydrate. You want to do this in 5 minutes or 10 minutes, otherwise the reactor size will be too big and it can't be scaled up actually. So these are some of the things. I'm not going to talk a lot on all of these, but I'll just quickly show you some of the data or the results which we have seen and some of the interesting facts which we have seen, and would like to seek some of your advice on some of those things. So basically you see here that there is a flow assurance. If this end of the pipeline is plugged by hydrate, then you see that there will be a lot of fatal accidents which will happen in industry. And oil and gas industry basically produces millions of dollars of oil every day. And if even one pipeline gets burst because of clogging of this pipeline, so it's $1 million industry. A lot of pretty much all oil and gas industries have invested huge amount of money in identifying a good inhibitor. Initially, people were basically using antifreeze molecules like alcohols or salts. But now with the oil being coming out with a lot of water cut, around 50 to 60% of the oil, it basically comes with water. So alcohols or similar molecules does not work anymore, because that creates a lot of inventory. So you need some smaller molecule which can be utilized only at less than 1 weight percent or 0.1 weight percent kind of concentration, which either can inhibit the nucleation of the hydrate, or if it can't inhibit the nucleation of hydrate, then at least it should not allow the hydrate to agglomerate or plug the pipeline in the process. So basically you can delay the growth of hydrate with some of these additives. So some experiments which you can do in the lab. This is a very simple setup which we had. So this is a stainless steel block, and in between we have a transparent reactor where we can basically see the morphology of the hydrate growth. So the experiment is done like this. You basically reduce the temperature. These are the phase equilibrium. Inside the equilibrium, this is the temperature and pressure which would be required for the hydrate to form. So you basically give some driving force for the hydrate to basically form, mix it, hydrates will grow, and then you dissociate the hydrate. And then you start observing the growth of the hydrate when there is no mixing, so that it's easier for us to look into the morphology. Otherwise, when there is a stirring going on, the morphology information will be lost actually. So hydrates were formed with natural gas. And if you see in this particular case here, you have formed hydrate with pure water, and hydrate starts growing at certain rate. It nucleates over here and grows over here. But in presence of these inhibitors, you see there is a long induction time, or nucleation point is much larger. It's around 200 minutes. But the rate of hydrate growth is very similar to what you see. So in this case, basically you have identified an additive which enhances the nucleation point. So what basically you are trying to do is that this hydrate, when there is at the source, when you're getting some oil, and this is the point where you will be getting the out for processing. If there is enough delay, then your oil which comes out from here will basically come out from here without getting clogged. So if you can somehow enhance the nucleation point or induction time, you will be able to maintain flow assurance. The other way is that you can reduce the kinetics of hydrate growth. So you see there are multiple additives which basically reduces the kinetics of hydrate growth. In this particular case, there are some additives which does both. It not only enhances the nucleation time, but it also reduces the kinetics of hydrate growth. Now let's look into some of the interesting facts. So you do an experiment with a gas. This is methane and propane mixture, because this typically simulates the natural gas in the nature. You have an interface which is over here. You see that there is an interface of liquid and gas. So as I was telling, there is a maximum concentration of gas and liquid at the interface. So you'd expect the hydrate to nucleate on the interface. But many a times we will see in this particular case over here, you see there is a pool of liquid over here. So the question is whether hydrates will nucleate in the bulk phase also or not. For that, we basically generated an interface in the between, in the middle of the reactor. And you see, this is the kind of arrangement we have. You have liquid water, and then in between we have a stainless steel mesh, which basically creates interface within the bulk liquid actually. And then we form hydrate, and you will see that hydrate not only forms on the interface over here, but it also forms in equal amount in the bulk of the liquid. Now, there is a very interesting problem over here. You see, methane dissolves in water at a very low concentration, 2.55 into 10⁻⁻⁵ molar. But when it forms hydrate, it has to be in 0.167 molar in concentration. It means even 1% of this water, when it gets converted into hydrate, all the methane which was dissolved in this liquid will get converted, will go into the hydrate phase. So where does that extra methane comes from? That is something which is very interesting. You see, there is around 10 to 20% of hydrate water which has got converted over here. And you will see there is no stirring going on in this particular reactor, and still there is hydrate forming. And this forming, this section is seen over here. You see there is a large amount of hydrate which has formed. That is something which is very interesting. I'll show you some more data. You see, what we are talking about here, 0.16 molar in solid hydrate. If you want to just get that kind of solubility of methane, you have to go to 1.5 gigapascal. That is around 15,000 bar. We are talking about just 30 bar. In 30 bar, we are achieving this kind of concentration. So obviously, there is diffusion of methane from the gas phase to the liquid phase, even after when there is a bulk of hydrate on the interface, which is, if you take out this hydrate, it will look like ice. It will be very solid ice, and you will not really assume that some gas will diffuse through it actually at kind of temperature which we are telling here at around 1.5 degrees centigrade. So that is interesting. What else you see? That hydrates keep growing for hours even after a thick layer of hydrate has formed on the interface. So you see here 90 minutes also you will see hydrates are growing. And lot of floating crystals you will see which basically comes from the bottom of the reactor, not from the interface over here. You see there are some crystals over here. You are seeing it's floating. It's all basically nucleated in the bulk water. And this bulk water is supposed to have no methane because it has already been consumed. Whatever little methane was there in the dissolved phase. You see there are different kind of hydrates which will grow. Basically these surfaces get cooled and then it grows in this direction. So there are different kind of crystals which will you will find. Now let's look into what happens when you use some additives. Now, as we were telling that we are using an additive which is polyvinyl pyrrolidone, which is a known inhibitor of hydrate. And you see the hydrate is, instead of growing in a straight line, you see there is a zigzag fashion of hydrate growth. So basically what happens there, once hydrate grows to a certain extent, this PV molecules somehow get adsorbed on the surface, and then hydrate has to grow in some other direction. So this is the kind of zigzag pattern you will see when hydrate basically grow. From the literature, I found that this is how they basically explain it. Jobson inhibition is what they typically call. I don't believe in many of these things though, but the point is that, yeah, there are some concepts which people talk about. Within the same hydrate layer, this is hydrate layer, at the interface, you see above this, you have a very solid hydrate. Below this, there is hydrates which are growing. It is attached to this interface, and it's somehow sucking the gas from this solid hydrate interface. But within the layer, you will see at one corner, there will be no growth of hydrate. And on the other corner, this will start going to a very large crystal structure, depending upon how you look at it. The morphology of the hydrate also is quite different when you have some additives in there. So in this particular case, these crystals which was floating from the bottom, still you see that, but it looks very different now. It goes and attaches itself to the inside of the interface, and then it sucks gas from the interface somehow, and then you see that it grows over a period of time. And you keep waiting and it will keep growing. I mean, it's not that the other interesting fact we saw was that hydrates basically also nucleates at the bottom of the reactor, where if you talk about natural convection, given the height of this particular reactor with natural convection, it would take days for the gas to diffuse from the interface to the bottom of the reactor. And you will see that these hydrates are actually growing, nucleating at the interface, and actually it looks like more tadpoles. They will just keep moving up. You see 100 minutes it is over here, then it has moved up over here, it has moved up over here, because these hydrates are slightly lighter in weight and they keep moving up actually when you wait for some time.
So Rajneesh, 20 minutes, huh?
Yeah, I will just quickly. So the most interesting fact we saw here in this particular case. Now, again, let me remind you that we are at 1.5 degrees centigrade and we are looking at the interface. And then you see suddenly this interface, the water starts evaporating. At 1.5 degrees centigrade, this interface moves from here to here. Then in 1 minute, then another 1 minute, it moves from here to here. And ultimately, when hydrate has actually formed, you see that there is a hydrate layer on the top of the reactor. And the liquid is over here, and there is no visual connection between this liquid interface and the hydrate. So depending upon what concentration you use in the additive, you will see that different kind of hydrates may form actually. And this is really surprising because the hydrates basically is not nucleating on the interface. They are nucleating somewhere at the top, and then it goes from the top to the bottom. And at the end, you see there is a big separation of hydrate and crystals. We thought it could be due to contamination. So we inside our reactor, we put another reactor and then we put some water. But still you see there are hydrates which are formed in the vapor phase. So these are some of the interesting observations we have. And then we did some MD simulations to figure that out, what basically happens when you have additives. So we see that when you have additives, there are a lot of case defects which forms. Very unusual type of cases forms. And those case defects basically enhances the diffusion of methane through the structure. We also found that in presence of these PVP molecules, you see there is an agglomeration or there is basically concentration of methane molecules. Now, whether these methane molecules concentrates in presence of PVP because of the surface tension effect of the water or mainly because it gets attracted to the large PVP molecule, there are still some questions remaining over there. But now we have basically identified, we don't understand a lot, but we have identified multiple additives which basically does multiple things. So some hydrates will form below the interface, some will form above the interface, and then some additives will actually form both places. You see, within seconds, you will see the entire water without stirring will get converted into hydrate. And it's not only at the bottom of the reactor or top of the reactor, it will be throughout the reactor. We have used some of these aspects. So for example, when your hydrate is not forming in the bulk liquid, you can basically expect the hydrate to go above. So if you have salt contaminated water, salt will remain behind over here. All the hydrate will form on the top of it and you can separate this out and you have pure water. So you can use it for desalination. This is something which we are also now working with industry. You can basically, with these additives, you can enhance the rate of hydrate growth significantly. You can store this hydrate at much lower temperature and pressure conditions compared to CNG and LNG. And if you look into the Raman spectra of some of these hydrate in presence of tryptophan, which is an additive, you also see that there is a very interesting phenomena. I don't have time today. We'll discuss some of these things. We basically also do a lot of applied research, as I was telling you. So we form hydrate, we dissociate hydrate in presence of our additives, and basically this can save millions of rupees like every hour for industry if you use some of these additives to basically dissociate hydrates under the seabed. We are also looking into CO2 sequestration under the seabed. For that, we have pilot reactors where you have injection well, production well, and all. And basically, you can use some additives and then CO2, which can go under the seabed, 50 to 100 meters below the seabed, and will get converted into solid hydrate without basically getting released into the atmosphere. So some of these things, there are many other similar interesting points like memory, hydrate memory. If you are forming hydrate with fresh water, it takes long induction time. But if you are forming hydrate with memory water, it will be much smaller. It will take the induction time reduces significantly. Some of those things basically surface gets some kind of memory. We will talk about it maybe in some other presentation. But these are the acknowledgement. We are funded by industries and government equally. All these work are being done by students. So I'm sure this is some simulation of NAC, and this is the experimental outcome of NAC building. So you see in experimental outcome, you see a lot of interesting facts. Thank you very much.
Very nice, Rajneesh. So let me just start with one question that you talked about how gas transport happens after hydrates are nucleated. You still don't know.
We know. It's not that we don't know, because as I was telling you, that we design many of these additives because we know to certain things. But I'm not saying that I'm an expert in this, and this is when I expect people from the chemistry department or from the physics department to basically help me out to understand it even better. So as I was telling you, there are case defects which happens in presence of certain additives. Because those cases are not of the type which you basically see. So inside this hydrate, even though it looks like very solid ice-like, there are channels. And there is also, I would show you this particular slide over here. When you form a structure to hydrate, you see here there is a channel within this structure actually. So the large cages, unlike this, where when a molecule has to diffuse, it has to cross two different kind of cages. In a structure 2, a molecule does not need to cross two different kind of cages. Within from the one type of cage, it can just diffuse out actually. So we do understand to certain extent, but yeah, I am not and still not sure that I understand it completely.
So one thing that you said is that there are a large number of hydrates and large number of additives. So when you start looking at this diffusion problem, or when the molecules are passing through the solid phase, do you have some correlations with the molecular weights of these hydrate forming molecules? Some of them move faster, slower.
Yeah, very good question, Professor Pradeep. So we have seen that hydrogen or nitrogen will move much faster compared to say methane or propane. So in this particular case, for example, when we did this work, we figured out we figured out that you need to have propane and methane both if hydrate has to go up there, and because propane basically pulls off the molecule, and then methane diffuse through the molecule, being a smaller in size actually. So we do have all this information with us at this moment. So we can also use nitrogen in presence of methane, and it will do the same thing.
So what it appears is that really a model, a kinetic model of how these hydrate nucleation propagates. There are gaps, but these gaps can be filled with the available data and theoretical insights. Greater collaboration is needed and more time is needed for that discussion. So let us move on, and Sundar has a question.
Yes, Sundar.
Hey, hi Rajneesh. It was really nice talk. Although I don't have much knowledge on the other part of the first part where you're talking about the gas hydrates, the molecular level. I just wanted to know what kind of interaction you have in the smaller cages and the largest cages. Is there only the hydrogen bonding, or you have different kind of interactions?
So the water molecules will be held together by just hydrogen bonding, and the gases will be entrapped there by van der Waals interaction, nothing more than that.
So like if you have a propane, carbon dioxide, methane, so they have all different kind of, like the cages, right? So how you can predict, is there any prediction that it could be like this or that?
Yeah. So there are thermodynamic predictions. So basically, there is models which basically can predict it. So you have basically three-phase equilibrium model where you the solid phase is modeled by kind of an empty cage ice van der Waal and Plateau model. So you basically model the solid phase by van der Waal and Plateau model, and then liquid phase and gas phase can be modeled by different equations of the state, and you can basically predict the temperature and pressure conditions at which these hydrates will.
Under this the conditions that is, as you said, that the seabed, all this kind of molecular, the hydrates are there. So can you apply them and you can make a model in the lab and make them?
Yes. This is all the lab done only actually. These all crystals you see here have been synthesized in the lab only.
And that you see a very strong correlation with the one which is the nature of the seabed.
We do the Raman analysis for the one collected from the nature as well as from the lab, and you will see there is no difference at all.
Only 50 meters away from Sundar's lab.
Okay, nice. Actually, excuse me because asking all these silly questions.
No. It was really interesting, and we can discuss more on this. And I certainly want to learn from all the people in the chemistry because that is something which will be very essential. Yeah, sorry.
Rajneesh, I have a lot of metal hydride clusters. I was thinking what else can be done with them.
Perfect. We can come. I can come and discuss with you, Professor Ghosh.
Sure. Okay. Thank you.
Thank you very much.
All right, people, are there other questions? One of the things that the subject area needs is high quality spectroscopy, and maybe there is something that all of you together can do, extreme experiments. I mean, we are doing something, but Manu and people like that who are in the physics department could explore new experiments in hydrates.
Yeah, this is why I basically presented this, and there are many similar interesting points on hydrates, and which we can certainly discuss one-to-one.
All right, and maybe, I don't know, at some point in time, we will be having experimental tools in the laboratory where we can cut an hydrate crystal and then look at it under atom probe tomography, and maybe low temperature experiments.
Yes.
My namesake is here, and so I don't know what he feels about such experiments. Dr. KG Pradeep. Okay, let us move on, and we have Srinivas next.
Yeah, hi, Pradeep.
Yeah, 7:39 now. Yeah.
Can you see the slides?
Yes, and we can hear you also.
Okay, correct.
Not full screen though.
Yeah.
There is a question here. Krishnarka has asked. In the meanwhile, can you please see it?
Yeah, I will. I will answer that.
Okay, go ahead. 1 minute.
Yeah, hi. Yeah, so first of all, good evening, everybody, and thanks to Professor Pradeep for organizing this event. So I'll try to make my talk a bit general because I'm not sure how many people will be related to neuroscience and related areas. So I'll talk about a problem that we are very passionate about in our lab, the need to simplify the theory of brain. So our overall goal in our lab is to build a simplified model of the whole brain and to use it to develop applications in medicine and engineering. So this is like a holy grail for the lab, for like a North Star. And so the simplified brain model, so whole brain, human brain has about 100 billion neurons. So this simplified model, we conceive it to have something like 10 million neurons. But it will have all the major components of the mammalian brain. So this is like a cartoon picture that we developed for brain. So there is a sensory input that you see on the right side going up, and the motor output on the left side coming down or going out. And the sensory input is like touch, vision, and all these things. And this information climbs through a bunch of areas in the brain, and at higher levels it creates representations of language and space and things like that. On the motor side, you control your arms and speech and eye movements and things like that. Between the two, you have this huge area called the prefrontal area, which is like the front of the brain, where decisions are made, planning, and all these things are done. And there are three major loops: the cerebellum, basal ganglia, and hippocampus. So if you have these main structures, that's like a skeleton of the brain. The rest is detail. I'm super simplifying it, but I think if you can make a model of these structures and with the slightly simplified computational elements, and that will be a major development because there are people, there are groups which are trying to build literally the brain neuron by neuron and fiber by fiber, with extreme detail, the very expensive efforts. And I feel the simplified model would be more appropriate in terms of its ability to deliver applications. So in the lab, we work on there's many different areas of brain function. So basal ganglia and spatial navigation and modeling neuronal oscillations and so on and so forth. You can get information from our lab website. So the main vision or the perception of a problem in neuroscience that we see, right, is what drives our whole approach and our whole activity. So what's happening right now is in contemporary neuroscience, it's very data intensive because since we have lots of fancy experimental methods, people keep on churning out data, like at various levels, like molecular, cellular, and behavior, and systems, and so on. So because of this, especially there's a lot of knowledge or data at molecular and cellular level. But when it comes to understanding at systems level, large scale, order of centimeters and tens of centimeters, our understanding of systems is somewhat poor, and it's quite development is quite lopsided because the theory is somewhat weak. Lots of theory is more like curve fitting type theory, and you don't have deep theories like the basic Maxwell equations or laws of thermodynamics. Those kinds of laws of the brain are still not found. At least we don't have the full set of them yet. So there are a lot of people who are expressing this kind of dissatisfaction. One of them is V.S. Ramachandran, who says we are still at the Faraday stage in neuroscience. Another is Patricia Churchland, a neuroscientist and neurophilosopher, who says there are no good neural theories. And many people have said similar things. So one problem is that the way biologists approach biological systems, the problem of reductionism. Because they want to explain everything in terms of the smallest constituent, which is typically molecules and cells. In this case, neurons. Whereas that won't work because engineers don't have that kind of a problem. Because if you want to say, for example, study the thrust, the pressure of wind flow on an aircraft wing, you don't try to model the molecular dynamic simulations. You try to invoke this kind of abstraction called fluid, right? And then use Navier-Stokes equation, and then you can get your work done. So whereas that doesn't happen very often, there's no clear framework for doing that in a rigorous fashion. So therefore, there's a lot of data at molecular and cell level, whereas systems level things are a bit vague. So this vagueness also translates into our inability to treat diseases in an effective fashion. For example, if you look at complex diseases like bipolar disorder, or schizophrenia, or depression, Alzheimer's, Parkinson's. So we have lots of patchwork of theory, huge mountains of data, but no effective treatment. In fact, other than problems that involve a simple surgical intervention or like kind of an infectious disease where there's a bug and you have to kill the bug, I can't think of a single neurological disorder or neuropsychiatric disorder where you can say that I can cure the disease completely, perfectly. So there's a fundamental problem with the field itself. So I feel that if we can develop simplified models, embodying the right kind of abstraction, which is very important, right? The right way to look at this phenomenon, and the way we do it in physics and engineering, I think that can be very effective, and it will have a huge impact in brain science. So to that end, we have made some humble efforts. I've written this book called Demystifying the Brain, which tries to present the contemporary computational perspective of the brain to a biologist, and also the same perspective also to an engineer without using too much of biological jargon. It's like we try to strike a balance between the two. So we work on many topics in neuroscience because the ultimate goal is not just focus on one thing and beat it to death, but have an integrative approach and develop many strands of research and integrate them toward over a long period of time and create this kind of a whole brain model. So one of the things we've been working on for a long time, like almost 10-15 years, is basal ganglia and Parkinson's. Other areas include hippocampus and spatial navigation, stroke rehabilitation using virtual reality, brain dynamics using nonlinear oscillators, vision, and so on. So basal ganglia, this is actually a deep brain circuit. Brain has a sheet of neurons covering the entire brain surface, which is called the cortex. So cortex is a major area in the brain, and inside the brain, deep inside the brain, under the cortex, you have structures which are called subcortical structures. And so one of these subcortical structures or subcortical circuits is the basal ganglia, which has many components or many modules. If you lay out these modules in a neat block diagram, it looks like this. So there is input coming from the cortex and this big sheet of neurons to the basal ganglia, and output from basal ganglia also goes back to the cortex. So the input comes to this kind of input port called the striatum, and output of it goes from two output ports, the GPI and SNR. It goes back to a big hub called thalamus and back to cortex. Okay, there's a bunch of anatomy inside. I'll skip that. There's a big important cell cluster called session-2 or substance nigra pars compacta, which reduces a substance called dopamine. So in Parkinson's, cells here start dying for some unknown reason. So it's called idiopathic. We have a fancy name for that called idiopathic. And because of that, you see all these symptoms. And it's PD is a progressive neurodegenerative disorder, because once this degeneration starts, there's no looking back, and whatever treatments you apply, they might slow down the process a little bit, but there's no question of complete arresting of the disease. So the major symptoms of this disease include tremor, rigidity, and postural. But devastating that it will affect pretty much everything that the brain does. The four major brain the function domains of brain function, sensory motor function, and cognitive, and affective, and autonomic. All these areas are affected. So if you look at a simple picture of basal ganglia function, which is kind of the textbook picture right now, is that there are two pathways in this: the direct pathway and indirect pathway. The direct pathway is activated; that facilitates movement, and indirect pathway is activated, that kind of inhibits the movement. And this switching between direct pathway and indirect pathway is done by release of this chemical called dopamine, and that this switching occurs because of certain molecular and cellular machinery that is available inside the striatum. I'm skipping all the details because it will take too much time to develop all this in detail. So we have over first 5 years, 6 years of study, we kind of saw that there's a problem with that kind of a picture that needs expansion seriously. And we propose that in the indirect pathway has another function also, right, which we call exploration. So we have applied ideas from reinforcement learning, which is a branch of machine learning, and also is inspired by animal learning. So a lot of people have done that. We're not the first people to do that. But we have applied that thoroughly to this circuit and did a mapping of which component in the basal ganglia corresponds to which component in the reinforcement learning framework. So we propose that there are 3 regimes in the basal ganglia: go, explore, and no go. And with that, we have created some kind of a unified model of basal ganglia, with which we were able to explain a wide variety of motor functions of the basal ganglia and also some cognitive functions. And we published a series of papers looking at different functions of basal ganglia, both in normal conditions and in disease conditions, which is mainly Parkinson's disease. And we have summarized all that, consolidated all that research, worked out over about 4 or 5 PhDs in this book, which was published a few years ago. And after this book, about 5 years ago, we started looking at different problems. That is, earlier we thought that we were assuming that the SNC neurons are somehow dying. We don't know why. What are the consequences? Then with this thesis of Vignan, we started looking at the different question, which is, why are the cells dying in the first place? What's wrong with them, right? Genetics cannot be the real answer, because about 30 genes are implicated in PD, so it cannot be a purely genetic disorder. So something else is going on. So the people have proposed that one of the reasons is metabolic deficiency. These cells are somehow kind of there's a shortage of energy, right? So we wanted to explore this using detailed computation models, and we have Vignan has done a series of models at multiple scales, at subcellular level, at cellular level, and network level. In all the cases, consistently we saw a kind of a common pattern, which is that if you squeeze the feed, if you constrain the feed of energy, that is glucose and oxygen, into the network, right, and you see a lot of pathology that you observe in PD can be observed in the simulations at all these scales. So, our on the clinical side, on the application side, our goal is to create a more quantitative and rigorous kind of framework for testing PD patients' condition. Because right now there's something called UPDRS score, where they score the level of abnormality of a PD patient, but it's very subjective. So we wanted to actually collect more rigorous data from the patient in terms of gait movement, speech output, eye movements, handwriting samples, right, reaching performance. How do you move the hand to reach to a target, decision-making performance to special gambling tasks, right? We make the patient do all this and collect this data, and you can collect all this using a mobile, and put this data into our model and kind of invert the data and extract some model parameters, very high-level meta parameters. And using the meta parameters, you can profile the patient, right, very precisely and rigorously. And then whatever treatments you want to give to the patient, you first give it to the model, right? And then if it works with the model, then hopefully it will work with the patient. We want to create that kind of a very scientific and quantitative framework, test bed for planning treatment for the patients. Right now, it's all very hit and trial, very kind of experience-based empirical kind of treatment, not very scientific. We want to create a concrete quantitative framework for doing that. So there is a field called computational neuropharmacology where you try to understand drug action not just at molecular level simulations, but also develop detailed multi-scale models to understand drug action not at molecular level, just at molecular level, but higher levels at cell and network and all the way to behavior. So we have done one such model just recently, submitted it to PLOS-COMP, awaiting results. So the next model, where we have been spent almost 5-6 years already, is modeling understanding hippocampus and spatial cells. Hippocampus is located inside the temporal lobe. You can see in this picture here that blue structure is hippocampus. Inside that, there's a bunch of clusters of cells which form the hippocampal complex. Hippocampus is important because it is involved in spatial navigation, and you know that rats and mice are very good at spatial skills. If you put them in a maze, they can escape, run around, escape, and find escape routes very quickly. So that capability comes from hippocampus, and that has attracted people for a long time. But in the recent times, in 1914, it's become really very hot because two studies in this area of hippocampus and spatial navigation, which are performed one was performed in 1971. So these guys have, John O'Keefe and Rostowski have discovered these cells called place cells in hippocampus, which fire whenever the animal is at certain location in the maze. And in 2005, the Norwegian couple, May-Britt Moser and Edward Moser, have discovered another kind of cells called grid cells, which fire not just at one location, but a whole bunch of locations. What is interesting is all these locations form a very nice periodic grid, which is often a hexagonal grid. So that was quite intriguing, because brain is a very messy area, and how could you find such nice geometric symmetries, right, in emerging out of such messy circuits? So this Nobel Prize has, suddenly increased the glamour of this area, and a lot of people started, jumping in and doing a lot of work. So we have also looked at, did some theoretical studies on this. So this video, I'll just play a bit part of it just to give an idea of what a place cell is. So here is the rat. There's an electrode sitting inside the rat's hippocampus, and actually measuring activity of a single neuron. So whenever the rat goes to that part of the box, you see that red dot indicates that that neuron has fired briefly. All right. So you see that that neuron is encoding that location. It's telling the animal that it's at that location. So so this is called, that's why this structure is called the GPS of the brain, more popularly just what it is called. So we propose a very simple model. The main thing that we have done is use of oscillators. So we propose that the head direction of the animal is encoded in the form of some kind of frequency modulation of a bunch of oscillators. And after that, certain standard neural network elements, which is part of standard theory, right? We did that, and we found that the response of neurons look a lot like the grid cells. Not only six hexagonal grid cells, the network shows lots of other kind of periodicities, square grid cells, octagonal grid cells, and so on. Then we also worked out a theory that tells you under what conditions you get what kind of periodicity. You can get any even number of even numbered periodicity. And then we developed the model further and added locomotion also as input, and then we found that there's a hierarchical organization in this way the neurons respond. Lower layers found to respond with a grid-like periodicity, whereas the higher layers respond with they behave more like place cells. Also, you have all these other mixed cases where a cell responds at two locations and all that. And actually, real cells do have these kinds of funky cases, and network also shows all these features. So then we extended this model to 3D navigation. So for this, we collaborated with a person from Berkeley, Michael Yartsev, who works on bat navigation. How do bats, since bats can fly, they move in 3D space. So bat is a mammal, so they have hippocampus and all that. They also have bat hippocampus also has place cells, just like say rats and mice or humans, right? And these place cells are kind of anisotropic and so on. So lots of studies have been done on that. So we extended our previous model with just adding one more feature, which is that in the previous model, the animal moves in 2D space. So there's only azimuth angle, whereas now the agent moves in vertically also. So there's a pitch angle. That's all we have representations for that. And otherwise, the model is very similar to the previous model. And here also we found place cells emerging. So they are also anisotropic, like what people have observed experimentally. But what is interesting is we found a new kind of cell, which is very fascinating, which is a cell which fires whenever the agent or the flying agent process a plane, right? We call it a plane cell, which can have interesting biological interpretation or a purpose, because if the plane is horizontal, then this cell can be thought to represent the altitude, right, of the animal, or for example, if it is a bird, it can represent the altitude. We also found another kind of cell in the simulations, which we call the stack cell. This is a cell which fires not at just one plane, but at any of multiple set of planes, right? So, or a stack of planes, we call it a stack cell. So now my student Karthik, who worked on this for his PhD, after PhD, he joined my Yardsafe's lab, and he actually did find plane cells after doing analysis of prior data from Yardsafe's lab. But stack cells are yet to be discovered. And so that's the kind of thing we've done several other things, but there's no time to discuss any of that stuff. So basically, what I want to say is, like, we have over the years we have developed this kind of philosophy of modeling, which is that there is no point developing extremely detailed models of the brain and trying to understand every cell type and all that, because you'll be lost in the details. Whereas I think the model should be sufficiently simple that so simple that if you make any further simplification, it will be absurd, like this Gandhiji's cartoon here. And you need to unify in the sense that the same model should be able to explain a wide variety of experimental data. That's when you say that the model is reasonable. Then once you have that, I think the model will be fit enough to to be applied to whether to explain more biological phenomena or for clinical applications by developing disease models, or for engineering applications. Now, another thing I want to say here is, so a lot of there's two kinds of neuron models which are very popular. That is, one is rate-coded model, another is spiking neuron model. Now there is a third there's another school of thought which says that the basic unit of computation in the brain is not a single neuron, but actually a pool of neurons, like a bunch of neurons. So what's called a neural ensemble. If that is the case, then the activity of these neurons will not look like voltage spikes, but look like a smoother signal, like an oscillation. So you can I strongly feel that that's where you need to put your money. I mean, that's really very potential with lots of splendid theory that can be developed. So we have started working on those lines a few years ago, and I have a PhD student, Deepa and Biswas, working in this area. So we are looking at networks of nonlinear oscillators, like hop oscillators, listed in complex domain. And we want to really work out a grand theory to look at many different aspects of brain function and explain them using these kinds of network models. So this will also be excellent link to deep learning, because this will be like a oscillatory deep networks. So we're using such network, we want to explain many topics in brain function. So we also want to kind of embody a lot of systems that we have been developing in a robotic embodiment. So we have a reaching model, we have a model of navigation, we have a model of locomotion rhythms. We have a model of visual attentional search, and we also begun some collaboration with Dr. Anindita Sahu, who is in humanities, who is a linguist in humanities. So we are looking at language modeling with her. So we want to put all this together and create an embodiment, a robotic embodiment, and I'm talking to Niti Aayog to fund this research. So the grand challenge is to create this kind of a simplified brain model and develop applications in medicine, for example, Parkinson's, in Alzheimer's, stroke rehabilitation, post-traumatic stress disorder, hemi-neglect, something as simple as even stutter. How do you fix this using nice network models? So also in engineering domain, can you put this kind of a whole brain model, realize it in hardware, like a single motherboard, and then can you put it on a drone or a robo or driverless cars, and these are the kinds of things we're thinking. The long-term vision is to do research in neuroscience where theoretical developments become take the center stage, and you take data, experimental data from all different sources, and put them together in unified theoretical models. And out of such modeling efforts, you create startups addressing specific problems in neuroscience and develop clinical applications. So this is our team, a pretty happy team, and thank you. So I can take some questions.
Very nice talk. I mean, we are just at 22 minutes, and so we have some time for questions. So let me start off by asking something, maybe on the last slide of this giant vision side, that is slide number 49 or something. So one of the things that you presented many aspects of the complex brain and the network. And together we want to create a a holistic, a society with collectivism leads to something distinctly different from individuals than individuals. Of course, individual himself or herself has to perform as well. One of the larger problems of our society in comparison to another society is that Indian mind, many people say, do not help in collectivism. And there are institutions, institutional examples of all that across the country. And we say that is the Indian crab mind. Now, an institution such as this, at this kind of IOE kind of time scale period, a lot of good things that are happening around in different sectors. Is there some way by which a collective model can be put together to indicate how to enhance cohesion, collectivism for the larger good? Now, there are, of course, many components in this, and many of them are far beyond probably, the data that exists there may not be adequate to model it. But how do you respond to something of that kind? And if that is so, how do you take it beyond the institution? Can we start it at an institutional, departmental, or group level to build that?
Yeah, thanks, Pradeep. It's a very important question. A question I myself have been grappling with for almost a couple of decades now. So one problem is, with collaborations, I think, top-down approaches won't work. And if you say all these guys can work together and want to work together, it won't work. They have to grow organically by one-on-one connectivity and slowly build trust. So basically, each party should feel that the other person is not taking them for a ride. And that trust, once it builds, they can really work together, and it should be in a time-bound fashion. I mean, we'll work together on this problem for a few years and we are done. After that, if you are interested further, we'll renew the relationship and keep going on. But so that the people should be free to kind of couple and decouple as and when they like. And there should be an open atmosphere and transparent atmosphere. And if that can be there, and if there's sharing of credit and fruits of the research, it'll form. And it's forming now. I think the new generation is very different compared to some of the generations that I've seen in my early days here. There's a lot of insecurity and a lot of suspicion and distrust and all that. Now things are very different. People are very transparent and a lot more forthcoming, right? To try it out. So, and another thing I found is again the same insecurity shows up even in the intellectual field. If somebody proposes a new path, right, the people are not that easily willing to try it out, even consider it and think through it, unless it comes from some big shot, from some Nobel laureate or somebody in the West. People are not willing to look at even an idea. So that's, I think, is a serious problem here. Right, we can think through the problem and see, hey, I mean, is it reasonable or is it nonsense? So we can easily think through that if you have some expertise in the field. But people are very insecure, to even consider that. And once we go over these hang-ups, and which we have, I think, made a lot of progress in that area, in the last maybe 4 or 5 years, I think we can do that. And if we are bold enough and a sense of I feel a sense of outrage. I mean, you send a paper to a top journal, they reject it without even an editorial level, as if we're basically inferior. So all this really fills you with outrage, and I think we should also. I think in brain area we need very serious paradigm shifts. There's no point tweaking it a little bit more, just like what somebody else is doing, just because it's a hot thing right now. Because it's not paying off. Let me tell you the economics of neuroscience right now. So when billion-dollar projects were proposed in, say, US and Europe, we thought it's a big money. I mean, what is happening with all that, we don't know. Now people are talking about tens of billions of dollars. Where is all that money going? I think this kind of a excessive, intensive, exponential approach where you keep on churning data for its own sake, if it won't pay off, and that path is not right for India. What you need is some brilliant theorists who can see things very differently and see through all the complexity and see a very simple underlying pattern. I feel strongly that such patterns do exist. It is possible to create such elegant, beautiful brain theories, and which can also be converted into practical applications of, and make an immense impact. You can really create a revolution in neuroscience. There's no point. I mean, if I go to a conference like SFN, Society for Neuroscience Conference, where 30,000 people come, what do they do? It's like, you one more pebble, one more brick in a huge, structure. That's what they're coming with. That's what they're contributing. How long will you go on like that? It's a huge amount of activity with very little outcome. I mean, what the taxpayer gets, what the common, society, member of a society gets out of this huge effort is a joke. And I don't want to give more data because it looks almost scandalous. Because I think there is something seriously wrong with it. We need to change the outlook, change the perspective, and then do something radically different. We cannot go on like this.
Asked this question was because while such people like you are connecting all the dots here, and while there are great theories and management, giants talking about effectiveness of institutions, effectiveness of products, and not only management effectiveness, many other different organizational structural effectiveness and things like that. Why is it that we are not in a position to bring in those concepts and the new ideas from neuroscience to make a scientific institution function better for a national good or international good or in an area's good? So this is something that one has to look at today, particularly in the IOE timescale.
No, but Pradeep, sorry to interrupt. I just want to say, I proposed these ideas for a COE and IOE. It was rejected because some international experts said that all this doesn't make sense. No, what they are doing doesn't make sense to me. So no, who is right? Who is going to judge whom? So there's a fundamental problem. We take their judgment too seriously. This is our problem. We don't have confidence in ourselves, our own people.
This is something that we have to discuss separately, and if somebody is working against, then we have to correct that. I think that we have to do. Let us move on. I think this is a very important subject matter. I think we have organizational effectiveness through neuroscience has to come in. We have two questions. Let me just take the first one to Pallab, and who has raised his hand first, and then followed by Manu.
Hello, sir. Myself, Pallab. Very interesting presentation, sir. Although
Thank you.
It will be a very bit difficult for me to digest this thing because I'm not in this field.
Cool.
So my question might be a bit silly in this case. I don't know. I'm not sure. So,
no problem.
I'm an experimentalist and I do mass spectrometry, and I do look at small molecules, which is relevant to some of your cases, as you talked about, like PD patients. So I have seen papers like even our own lab seniors, they found some molecules in breath, which is found only for PD patients. Also, people do mass spectrometry based imaging techniques like desorption. Like there are many molecular imaging techniques to find out molecules or some cells which would distinguish than the normal and than the patient. So as you talked about the computational modeling of this different models. So how, my question is how these models would be helpful to the experimental results that we generally find in case of mass spectrometry, for example, or how our results would be beneficial to your models.
Hi, Pallab. Actually, I'm sorry to say that. See, my knowledge at this molecular level is very, very weak. I'm an engineer basically. I'm more comfortable at systems level. But so obviously, ultimately, the drug will act at molecular level, not at systems level is a very high level repercussion of that. But if I'm not very knowledgeable at the level at which you are talking.
One slide,
so
sorry, go ahead. Yeah, so just in one slide you have.
Yeah, so I'm not.
In one slide.
Yeah. So that.
Sorry, go ahead, sir.
See, what happens is that's a simpler case. So we looked at the effect of L-DOPA, which is a drug, right, on all the way at the symptom level. How does it change your reaching movements and all that? So at this level, the chemistry is, in fact, Vignan is more knowledgeable than me at this chemistry level. So he was able to handle this. And left to myself, I would have really had real trouble with this. So here what happens is the drug is uptaken by the cell, the SNC cell, and it is used as a part of the dopamine synthesis pathway. Right, so he has done all the chemical kinetics equations, and this is a simpler problem. But if you are looking at, so let's say, a dopamine agonist, which will act on a dopamine receptor, that will involve the kind of things that my colleagues in biotech department do in a molecular docking and drug ligand and receptor interaction, those kinds of things. So that's way beyond my expertise. But that kind of molecular level stuff must be done, and then you need to smoothly connect it to higher levels, right, and create a multi-scale model. But I'm not knowledgeable at that level. I'm sorry.
Okay. All right, Manu.
Thank you, Professor Chakravarti, for the very interesting talk.
It's just Srini, no Professor.
Okay.
Yeah.
Yes,
yeah.
So, though I could not follow much of it, but I have a question, a naive question on something you mentioned in the beginning about reductionism.
Yeah.
So, like all our human experience, sight, emotions, dreams, speech, thought, they are completely different. They are qualities and they cannot be compared with each other. But when we talk about a voltage signal, we are trying to quantify a quality. So what are the limitations from trying to quantify something which is essentially a quality?
Wow. Okay. So let me try to rephrase your terms, your question, just to make sure I understand this. Are you asking that, see, in the brain, all activity is just electrical activity or chemical activity? But when it comes to your experience, if you are looking at a scene, I get a visual experience. If somebody is touching me, I get a tactile experience and so on. How does the same electrical activity give you different experiences in different contexts? Is that what you're asking?
Right. I think one of the things is my experience is a quality, and science has a limitation that science only probes quantities. So when we say that we are probing
the numbers,
we are making an assumption that all qualities can be quantified. So it's an abstract philosophical question. Can all qualities be quantified?
No, it's not just quality. Here is a deeper problem, which is, see, you can always classify your numbers into some classes, and then you convert your numbers into qualities, right? That can be done, but there's an even deeper problem when it comes to this kind of so the consciousness theory, consciousness literature talks about, uses a term called qualia. Qualia means our experience, which is in terms of qualities, which is what you're talking about. How do these qualia come about? By the biophysical activity in the brain. The answer is nobody knows. People use these terms, but that link, how does one become the other? Nobody knows. At least not to my knowledge. That's one of the hottest problems in consciousness research.
So when wife says it is a green sari, there are hundreds and thousands of different shades of green sari.
Yeah.
And this, how do you register this green sari in the form of a particular green sari in the form of a molecular signal?
Okay, so thing is the rods and cones, right? The cones in the retina, which actually convert your light signal into color. From there to the perception level where you say this is green, this is blue and all that. I mean, there's so many stages. And the perception that you can identify at a cognitive level, it is very flawed. You can easily be fooled, right, by controlling your environment.
Ultimately, that particular green of that particular leaf, which I want to acquire from that particular shop, that green versus some other green, how do I register that as a molecular signal? Ultimately, it is registered and recalled.
Yeah, but what you are experiencing is not the molecular signal, but nth order representation after so many transformations.
Correct.
In the brain, that's what you are experiencing. You have no idea about, you cannot even correlate with what the cones record and what the, say, somewhere in V4, the area of the visual cortex, which processes color. There's huge gap.
Are you saying we cannot, or are you saying
no.
We are currently
that kind of a
position to?
Human being may not be able to classify that many colors because there's so many stages between your molecular machinery in the retina and the higher brain areas where you perceive color.
Sure, let us move on. I think we'll take more time. Abhijit, you have a question.
Yeah, hi. I had a general question because what you seem to be suggesting is that molecular level and finer level, there are there's lots of information, and there's a need for abstraction and to build a model.
Yeah.
The type of models that you talked about were sort of abstracted to the level where we are not talking about classical mechanics or classical electrodynamics. I mean, in the end, there may be some stresses involved. There is electric field, charge densities, flow. So is there any effort to sort of bridge the gap by, again, given the computational power we have now, I mean, can we again look at classical mechanics of brain?
No, it will be more like electrochemical models. But see, I'm not talking about that, Abhijit. The thing is, you can have this biophysical description of the brain, and a huge amount of models are available. If you want, you can simulate them using a supercomputer. But what will be more effective would be to convert them into abstract network models, right? The kinds of things that complex system people do, or machine learning people do.
Right.
But there you need also new concepts. The existing networks don't seem to be the right ones to describe brain dynamics. So that is where I feel a certain, a little paradigm shifting has to be done. Maybe use of nonlinear oscillators. And machine learning people don't use nonlinear oscillators. We don't even know how to put them in. All right. So yeah, so at that abstraction, things become somewhat easy.
Soumya, I mean, not Soumya. I think let me go back and Manu, you had some other question, and before I get to Soumya. Well, let us go to Soumya.
Hi, Srini. It's a very interesting talk. My name is
Soumya.
Hi.
Yeah. Hi,
so, though I understood a little bit, but what? So this looks like something like a kind of inverse problem where you see. I mean, when you're building the network, it actually gives the result. So basically, based on the result, you're making this network. Is it correct? What I understood?
That is one of the problems. For example, especially if you want to develop clinical applications.
Yeah.
Right. You measure some things from patient and then put it into the model and invert it.
Yeah. So in this case, basically, you I mean, it will change, right? System to system, or I mean. Whether it will be there will be any universal problem, or it will kind of change system to system, because
yeah, good question. So the thing is, if your model is super detailed and complex, so it will be futile to try to invert it. But what I'm saying is, if you develop certain simplified models, they can be parameterized and kind of fitted to a given patient or a given subject effectively. And in that, once you do that, you should be able to invert the model and get some meaningful numbers. If it's a super detailed model, then there's no question of inversion because it will be lost.
Okay.
So we have done some work on those lines. So for example, we have looked at it. Yeah. So if the model is sufficiently simple, your inversion has a chance to work. Otherwise, it will be just nonsense.
Okay. There are lots of collection and data collection and all these things are very important.
Yeah. If data has some 10,000 parameters, then if you try to invert, you will get some junk if you don't know what's going on.
Okay. Thank you.
All right. I don't think there are other questions, and so we are going to conclude this. And the next meeting, very nice, and thank you all of you. Thank you for joining. Although the attendance became thin after probably people went for dinner. But then that is what happens. So we'll proceed with our plan, irrespective of who participates and whatever. That has been my approach all along. So next meeting, we have May 22nd, and that is a Saturday. So let's get that fixed on May 22nd. And those of you who are hearing this next meeting, who are all speaking? Suraj? Well,
sir, 4 people are there. Dr. Soumya Datta, Dr. Ratnakumar Annabatla, Professor Ramesh Gardas, Dr. Tarak Patra.
Okay, all right. All the people have already responded, I suppose, and otherwise we will contact them.
Yes,
and
sir.
That's all. And as usual, we will announce this meeting and link, etc. You had a question? You had a question, Chaitanya? No.
No,
right.
no.
Thank you very much. Good night.
Thank you.
Thanks a lot. Good night, everyone.
Thanks.
Thank you.
Thank you and good night, everyone.
Thank you.